Hey guys, and welcome to this new tutorial on computer vision. In the first video here, we're going to talk about like an introduction to computer vision, and we're going to talk about like different types of cameras and like the configurations and specifications for cameras, and also like we need to know the basic stuff when we're talking about computer vision, about a frame and images, and also like pixels. So this video is more like the basic stuff and things you need to know when we're working with computer vision. The first slide here is like just a course tutorial overview, so you can see what kind of different different kind of topics we're going over in this tutorial. And I'll upload a new video every week, so there will be one new video in each of my tutorials. Right now I'm doing a algorithm and data structures tutorial in C++ and an artificial intelligence tutorial, and then this tutorial on computer vision in C++ as well. So there will be one new video every week in one of those tutorials. So in the first videos here, we're going to talk about like the basics of image processing, because we need to know the basics of images when we're going to like use them and do processing on them. So in this video here, we're talking about like different color models, and in the next one we're going to talk a bit about like noise and smoothing if we have a lot of noise in our image or video or anything like that. Like how can we remove noise and smooth out the image. Later on, we're going to talk about binary image processing when if we want to like have either 1 and 0, and we want to like threshold some value out. For example, we want to detect an object and we only want to show that object in the frame. Then we can do something that is called like binary image processing with thresholding and also like some other different kind of methods. Then we're going to talk about like 3D vision with camera models and stuff like that. And then in the later videos, we're going to talk about like edge detection, how we can detect edges on different kind of objects, and also like some features and recognition in terms of how we can detect like, for example, faces or like any objects, and how we can like go from detecting some objects to recognizing some objects. So we don't know like there's detected a person here, but then we know when we recognize them that this person is this person, like this is like this name and age and stuff like that. So we know which person is in the frame instead of just detecting a person in the frame. So just to like give you an overview over like this course and tutorial and what we're going to talk about in later videos the next upcoming weeks. So the first here in computer vision is like we need to define what is computer vision and also like talk about like what it is. So computer vision is about like how we understanding images, and they can either be like an image can either be a grayscale image, or we can have a color image or a multispectral image. And then when we're talking about like computer vision, we're taking in snapshots from, for example, a video, or like we are doing some processing on an image. And then we can also like do our processing on video sequences, where like video sequences is just like images that is going really fast, like 30 frames per second and stuff like that. And then there's also like we need some different kind of configurations if our camera is static or moving, or we have a scene that is static or dynamic. And then we can also like have a calibrated and uncalibrated camera. So like these are some of the important things to know as well. Like we can't just go into computer vision and do stuff. Like we need to know like the basic stuff, because we can't really get like precise image processing and stuff like that if we don't have a calibrated camera, or we don't know anything about like our camera environment or the scene. And then here there is like computer vision aims to extract useful information from images. So it's like we're given an image, and then we need to extract some kind of useful information from that image, like a human does. So like we're looking around with our eyes, and we are observing different kind of stuff. Like we can see like there's a car over here, there's a moving person over here, and stuff like that. And it's kind of the same with computer vision, where we get different kind of images or snapshots from the environment, and then we try to extract the information from that image, just like a normal human being is doing. And then like we're using computer vision for like inspection purposes in like industry, or analysis on an image. For example, if we want to analyze how many objects there is in the frame or image, stuff like that, but also like control purposes. then we need to define, and there's a lot of different definitions of computer vision. It's like really it's really widespread out. But like we have this kind of machine vision and industrial vision. Like I kind of see that it is as the same vision and like the same definition, where we use computer vision for machines and in the industry. So we can, like, for example, have computer vision that is doing some kind of like checking for, like, for example, if there's any fault or like any error on some kind of product that is going on in a factory and stuff like that. And then we can also like just have the normal computer vision, where it's just a broader term, but like more like processing of image data, which it says here. So like the boundary is not clear, but the main issues that lead to the term being used more than emphasis one, because like in computer vision it's like more widespread out. And it's just like more the underlying statistical property and shape models and theory-based algorithms and stuff like that. So it's more for like image processing and pattern recognition. And the last term here is the image analysis, where we can have like, it's more like of a general term, but it is mostly just like we do some analysis on the image, as I told you before, and then we try to extract some kind of useful information from that by doing some kind of operations on it. Then there's some different kind of examples here, like for motivation of why computer vision is important and why it's like really fun to learn. So on the left picture here, we can see that a car is moving with a camera, and then it can detect other cars in front of it or like behind it and stuff like that. So for autonomous driving, like this is a really important topic, because like we can almost have a like full autonomy car driving around, because it can detect lanes and it can detect cars and people walking around. Like on the right side here, we can have like some kind of other sensor than a camera that can detect like how long is there to the next car, or how many people are walking, what kind of direction is the people going towards, and stuff like that. So like those are like the kind of the most like crazy things you can do with computer vision, and they're also really important, and you need a lot of image analysis to perform those kind of operations. So it's just more like kind of an motivation for computer vision. Then go down to the like bit more theory behind the computer vision, because we can't just use computer vision. Like we need to know the theory and also like the concepts behind cameras and computer vision in general. So in this case here, we have like a camera, and like it's a pinhole model for cameras. So for example, let's say here we have our camera here, and then we have like the pinhole here, where like the light goes through. So we have our pinhole here, and then we have like our image plane down here, which will be inverted like the real human eye. And then it sees like some kind of object here, and then the lights get reflected through the pinhole, and it tries to display the object here on the image plane. And then we can like set up a matrix for this pinhole model and for cameras. So this should simulate like what happens in a camera, and this is like the lens that like the pinhole in the lens that the lights are going through. And then we can set up a matrix here where we can say that we have like our I and J is like the coordinate system for the camera, like the pinhole model. And then we can have like some kind of the focal length for the camera. So those are just some specifications I'll go through in the next slide here. And then we also like have a location of the optical center here. So like if we go more in depth with the camera specification here, like we can see that we have a camera here, and it can have a different kind of sensor type. The most commonly used ones are the CMOS sensor types. And if we look at the camera over here, we can see that we have a camera, and then we have like a length, and then we have like our pinhole inside here somewhere, and then we have the image plane as I showed you on the previous slide, and then we have like the focal length is out to like the pinhole. So the distance from the image plane to the focal plane is called f, and we just call that like the focal length. And then we can also like have an object here, and we have like our field of view is how wide we can see from our lens. So in this case, we will have like this will be our field of view here. So we can like if the object was over here, then we couldn't see it from the camera because we say that is out of the field of view of the camera. To calculate the field of view, we have like the D value here, which is the sensor size. So we need to know what size the sensor is, and we also like kind of know how we also need to know our camera resolution and pixels and stuff like that. But to calculate the F of view, field of view, we also need to know the WD here, which is the distance from the focal plane, so like from the lens and out to the object. And then we also need to know the F, which was the focal length here. So when we know all these three parameters, we can calculate the field of view. Or for example, let's say we were given the field of view from a camera, and we know like the focal length and also like for example the sensor size. Then we can just like move these parameters around, and then we can for example calculate the distance from the lens to an object, which in many cases we want to. For let's say a car driving around and it sees a car, then it can like calculate or like it can estimate how far away that the other car is. And then we're also going to talk about like images and pixels, because like these are the most fundamental and basic stuff in image processing. Like we need to know the basics of images and pixels before we can do some kind of operations on them, and also like how we should like choose our different kind of algorithms and know how we can like use the best algorithms and also like just methods on our images. So like an image is just like a continuous 2D functions where we have like an ij or a column row or xy. So it's like a coordinate system where we have like our x and y, and then we can like just have in the coordinates are just like corresponding to the pixels in the camera. In an image, we can have like a discrete representation. So we can, for example, take a sample or a quantize of an image, and then we're using that sample quantized to do some different kind of operations on. And then we also need to know, when we're doing our image analysis, we need to like think about how many number of samples we need, because if we have too many samples, we might waste time and computation time compared to like what kind of operations we want to do. So it's like a really important factor you need to think about. Like for example, if we look at the pictures over here, we have like some kind of building here, and then if we like downscale the resolution, we can see that we can still see like this is a building and this is still a building. And some algorithms, they can actually still see like that this is some kind of building, or there's like something in the picture. So we don't really need like a high resolution when we're doing image analysis and processing and just like different kind of operations on our image. So we need to take into account what type, how many samples we're taking in, like how many frames are we doing calculations on, and also like the resolution of the picture. And also like when we're doing quantization, if we want like 8 bits, or like most of the cameras they're using 10 bits, but like 8 bits is typically enough, because if we say that 8 bits, then we have like 255 different kind of possibilities for each pixels. So let's say like this pixel has 1,000 pixels, then we have like thousands times. Then each pixel will have like a value from 0 to 255 that corresponds to like for example, let's say we have a gray tone here, and then like the full gray tone will be 255 and 0 will be full white. So each pixel has a value, like a color value, let's say in that way, from 0 to 255. And if we had a color image, we will have 3 channels for the red, green, and blue. So each pixel would have like 3 values. Instead, if we grayscale them, it will only be 1 value, which I'll talk about later in this video. And just a small code example down here from the Open Computer Vision library, where we can take an image with this object here. Like we create an image object here, and also like a small image, and then we can use the built-in functions from OpenCV that is just called resize, and then we give the function the image we want to resize, and then we give the image where we want to store the resized image in. It could be in the same image here as well, but then it will not know the previous one. And then we need to give it a size. So in this case, we're just taking the columns of the first image, and then we're taking like the half of it. So like we're halving the resolution of this picture in this case. So another code example here of quantization, where we have a function here where we want to change the quantization to gray. And the first parameter the function takes is this image object, and then the second parameter is the numbers of bits, as I talked about on the previous slide, where we typically want 8 bits for our image. And then it's a good idea to, like the first line of code here in the function, to use the CV assert function here. And then because if none of these conditions, like one of these conditions are not true, then it will throw an exception and the program will terminate. And it's a good idea because in this case we're checking if the image type that is entered, like the image that is passed to the function, is of this type, like the CV 8 bits UC1, or like and the numbers of bits are greater than or equal to 1 or less than or equal to 8. So our image needs to be some specific type that we want to, and the bits has to be like between 1 and 8. And if that's not true, it will throw an exception and it will terminate the program. And it's a really good line of code to have in the start of the function, because if you, for example, are doing some calculations or some kind of operations on an image where you're using 10 bits but it was supposed to be 8 bits, then there will be some errors in the code and it's hard to debug and find where the errors occurred. So it's good to like throw an exception if it's not real, or like the image you want to do some operations on. And then the second line of code here, we have our mask, where we want to like quantize our image to gray, and we do it with this mask here. And then we have 2 for loops here running through the rows and columns in the image. And we're first running through all the columns in the image and then all the rows, because OpenCV, they store every column, like every row are stored side by side in the memory. So we go through all like the columns in one row, so each value will be beside each other in the memory, so our program will be faster and more memory efficient. And then we can use this function down here, like where we just say like add the image at the row and column, which will be a pixel. Then we AND that value, like that pixel value, we AND that with the mask, so we quantize it to gray. And that's how we like access individual pixels in an image and do operations on them. There's a lot of built-in functions in OpenCV where you can do all of these kind of things. But if you want to like take this example, just shows like how to take every single individual pixel in an image and do some kind of operation or calculation, or just a modification to that pixel, like how you can do it, and also like how you can do it in a fast and memory efficient way. In this case, we just change the quantization to gray, where we take each individual pixel and that pixel with the mask we set up here. Then like in computer vision, we have different kind of column models, and we can like, as I talked about, we can have like color and grayscale, where in grayscale we have like the luminance only, so it's a simple representation, but we can, like humans and computers, they can still understand the image at a really high level. So when we're doing, like as I wrote down here, like when we're doing our operations, we typically convert our image to grayscale and then do our operations and calculations on that grayscale image. And then when we want to represent our operations or our result, we do it on the colored image. So normally we just load in our image as a color image, and then we create a new image or frame, and then convert the previous image to a grayscale picture or image, and then we do the calculations in those. But when we like show or plot our image and result, we do it on the colored image. And then, as I said, like the colored image, it has multiple channels for color, so it has 3 channels, where the grayscale only has 1. So we need to do like 3 times as much many operations on colored images versus grayscale. And if we, for example, we had a video sequence, like we need to have a video sequence with 30 frames per second, then we need to like do a lot of calculations and also like not necessary calculations, because as I said, like humans and all the computers, they really understand grayscale images very good. As we can see down here, like we can see there's some people, there's some trees, a building, but we can still see it on the grayscale. So it will just it will just be a more complex process to do our operations and calculations on the image picture here compared to the grayscale one. Then we also have some different kind of color models, which I will not really go over in this video, but it's just to like list. We have different kind of color models we can convert to, or like change from and to. We'll talk about some of them in later videos, especially like the HLS images and also like the HSV, because in some cases they're very useful, and you need to know like different color models, because in some different examples or like situations you need one color model is better than the other, but like it just like needs the basic understanding and just like experience, and then you know to like when to use one of the other. So we're now jumped into Visual Studio, and I'm going to show you some different kind of examples of how to load in an image, and also like how to do some different and simple operations on images. And mainly you're going to use like the built-in functions from OpenCV that is already like tested a lot and stuff like that. But it's also really important to know how you can get every single pixel in an image and do some operations yourself on them. So in the first example here, we just like include all the libraries we need from the OpenCV library to do our operations and methods. And in the first one here, we just give it the image path here to the image we want to load in. So in this case, I want to load in an image from my image folder. And then this image folder is in the same directory as this project in Visual Studio. Then we can create a new object here, new image object here, and call the imread function from OpenCV. And then we can do the first argument here to the function is the image path. And then we give it a second parameter if we want to load it in, like for example as a color image, or we just directly want to load it in as a grayscale image. And we just load them in twice to like have some different kind of calculations on both. And then first of all, we start with checking if both images or one of the images are empty, because if they're empty, we couldn't load them in, and we'll just return 1 and terminate the program. Otherwise, we just go down here and we rotate the second image we loaded in. We rotate it by 90 degrees counterclockwise. So there's some different built-in functions that you can use from OpenCV, and you can go check out their documentation. Like they have good documentation and a lot of different kind of operations, and also like built-in functions. So in this case, we're just rotating our image by 90 degrees counterclockwise, and then we're resizing the image with this function as I showed you in the slides, and then we resize it to 500 by 500. And we just start with printing this out. We have like the image 2 first, and it will come here, and this is the second image. So later on we take every pixel and grayscale them, but in this case we just rotated the image. So this is the original image here, and then we rotated it and resized it on the second image here. So we just close these again by hitting some key. We can see that here I'm running through all the pixels in the image from like each row and each columns. Then we're going through all the pixels, and then we take like the BGR pixel. We calculate we just get all the values, like all the color values from all pixels in the image, and we just store them in this vec3b data type, which is a built-in data type for OpenCV. So this will store like the 3 color values. And then we can like take those 3 color values and grayscale them by this formula here. So we take like the red channel, green channel, and blue channel, and then we sum them all and divide by 3, and then we like then we grayscale the color value. So in this case here, we define our grayscale value here, where we just take it will be a single value, because when we have grayscale, we only have one channel from 0 to 255. We have 8 bits color resolution. So in this case, this will just return one value, which is the grayscale value. And then we can say that here with the image 2, we take the image and add the image like I and J. I is the rows and J is the columns. So this is all the pixels in the picture. So at all the pictures, like all the pixels in the picture, we set each each pixel to like the grayscale value. So we convert them from their BGR values. In OpenCV they use BGR, where normally we use RGB, so like just flip it around. But in this case we just convert our BGR values to a grayscale value, and then we set our grade pixel just to like print them out, but we don't want to do that now. So with this command here, we just converted all the pixels from a color channel to a grayscale channel. And down here we just wait for some key to be pressed, and when some key is pressed, we just terminate the program and return 0. So if we just run the program here again, we can see like the second image over here is rotated as before, and then we grayscaled the whole image compared to over here. We have the different colors here, and then we took each pixel here and converted those color channels to a grayscale value, and then we displayed the grayscale value over here on the flipped image. So like that's how you can do a simple like conversion between colors and grayscales, and also how you can access the individual pixels in an image and do operations and calculations and just like image analysis on the individual pixels in a picture. There's of course a built-in function for this as well in OpenCV, where you just like have CVT color, and then you give it some parameter that is like BGR2, like number 2, and then to gray. So this is more just like there's probably a built-in function for like every operation you probably like the basic concepts and operations you need to do on images. There's built-in functions for that in OpenCV, but it's more like just to give you some kind of like knowledge what's going on behind the scenes, and also so you know like what happens in the function, and you're not just using them without knowing what's going on. So yeah, that's pretty much it for this video, guys. I hope you enjoyed it and learned some new about computer vision and also OpenCV. It's really important to like know the basic concepts, and also like just the basic concepts and knowledge about cameras and configurations and how we do like the basic stuff, because then we can always like build on top of that. So yeah, I just really appreciate that you're watching this video and helping me grow in this channel. So remember to hit the subscribe button under the video, and also hit the bell notification so you will get a notification when I upload a new video to one of the tutorials I'm doing right now. As I said in the beginning of the video, I'm doing a new video in each of those playlists from every week, and currently I'm doing a computer vision, algorithm data structures, and artificial intelligence tutorial. So I hope you're following along with those as well, and then I'll just see you in the next video, guys. Bye for now.